Morning, everybody. I think we'll get started now, and if other people join, that's great. So thank you very much for coming back for day 2 of the East Africa Use and Interpretation of ECMWF Open Products training course. We hope you found yesterday interesting and helpful, and we also hope the same for today. Now, just a small point today is that we've changed the agenda slightly from one that you may have seen. To incorporate some of the feedback from yesterday. So you mentioned, a number of you mentioned about box plots and not understanding their interpretation. So we're going to be going through those. I'm going to go through those straight after this. We're then going to have an expert presentation on using ECMWF data in East Africa. So we have a couple of presenters here. We then got a break, and then instead of the practical session on making a forecast, we are going to be focusing instead on the EFI and cumulative distribution functions, including a practical session on these in the kind of second part of the session. And we hope this will really help with your interpretation of those plots. And then we're just going to end with a bit of a short feedback session, and then we'll be ending at midday UTC or 3 o'clock EAT. So I hope that's okay with you. So has anyone got any questions that they've thought about overnight that they'd like to ask immediately this morning? If you have, as always, please raise your hand or post in the chat, and we'll do our best to get back to you as soon as we can.
No talk.
No. Thank you very much.
I was just trying to go through the online product from ICMWF.
Mm-hmm.
But there is one I want you to explain more.
Okay.
The interpretation. When you go to EFI,
yes,
I was exploring EFI for Africa for these days,
mm-hmm.
and see that you have two maps. You have the one of EFI and the other one on the light side.
Yes.
So I want to know the real relationship between the two maps.
Okay, I'm just pulling one up. So we have.
Just now I have them. I don't know if I can share them.
Okay.
Which one to share? This one. Can you see my screen?
Yes, we can.
Yeah, now you can see this map. This is for the EFI.
Yes.
And this one on the right side. What is the relationship?
So the one on the right side is the model climate. So if you scroll down a little bit, you'll see a little more information in the text about model climate. So it's called M climate. So keep going, it's below shift of tails. And the model climate is what we're looking at when we're forecasting. So the EFI, as we mentioned yesterday, is relative to the model climate, because we don't want to be, it depends on where you are in the world. So for example, so this is is this precipitation, or is this, oh yeah, this is precipitation. So for example, in the desert in Africa, there's not any precipitation very often. So when there is say 10 millimeters of precipitation, that's a lot. Whereas 10 millimeters in England, we get that every day. So the model climate looks at it's reforecasts. So it's looking at the past and saying, right, this is what normally happens in this area. And then the EFI on the left-hand side is saying, right, compared to what normally happens, these areas are extreme. And the colors depend on how extreme they are. So the yellow colors are just saying there is something more than normal there. And when it gets to red, it's showing a lot of the ensemble members are saying we're actually going beyond what we would expect here. So the one on the right is saying this is what we would expect in an everyday situation. And that just helps you find those extremes, and it'll highlight the areas that you need to look into in more detail. So for example, a lot of the one on the left is over the ocean at the moment. So rain over the ocean, less impactful. But if you had I know Africa's had quite a lot of extreme rain shown in the EFI recently. So for example, over Lake Victoria, so in that area. So you'd say, right, the EFI is showing some extremes here. We'll look at the precipitation charts more to try and understand what this may mean and what the impacts may be to people there. So you'll always find the one on the right is saying this is what we would expect.
Thank you. I think I get it.
So I think Anna will be going through this in more detail after the break. So this afternoon, I think. So in the second part of the course today, we are going to be focusing on EFI and model climate and shift of tails. So hopefully that'll give you a bit more information.
Okay, thank you.
No problem. Great. Has anyone got any more comments or questions that they'd like to raise this morning before we get started with box plots? I can't see any, so we are going to get started. And here we go. So, so yesterday, Anna showed a box plot, and a number of you said that you didn't really fully understand how box plots work. So I've put together some presentation about box plots and how this relates to meteograms, because that's basically what meteograms are. They are a series of box plots in one per time step. So we are going to start very basic. And then we will build on it. So please stay with me. So box plots, you might also hear them known as box and whisker plots. They provide a visual summary of lots of data points. So they're quick for understanding the forecast uncertainty, or how confident you can be in a forecast, like and likely scenarios. And then also the extreme ends. They will show you extremes as well. So in meteorology, we do use them to summarize ensemble data. ECMWF has 51 ensemble members, and these kind of plots are used to summarize all that data coming out of the model. And these are called meteograms. So you'll always see meteograms will be vertical. So we'll be focusing on vertical box plots today. However, you might also see box plots in other, for example, scientific papers, and other things might be horizontal, but you can interpret them the same way. But as meteograms are all consisting of vertical box plots, we will be focusing on those today. So we're going to start with a very basic example of making a box plot. So first of all, we need some data. So we're just going to use a series of 15 numbers to make our first box plot. So the first thing we need to do is to sort these numbers into order. So it doesn't matter how many numbers or what numbers they are, but in order to make the box plot, they need to be sorted into order first. So that's what we've done here. So we're just going from 1 to 9. You can see some numbers occur more than others. So you can pretend this is rainfall amounts or number of apples you have in your bag or whatever you want, but we're just going to focus with numbers at the start. So this is our minimum value. Now we're going to start plotting our box plot. So I've got on the right hand side here a scale. So 0 at the top and 10 at the bottom. So we as it gets bigger, it descends. So we've got our minimum value of 1. So we can draw a line on our box plot that shows our minimum. Our maximum value is 9. So we draw another line on our axis, and that shows where the maximum is. If you take the minimum away from the maximum, you get the range. So in this case, 9 minus 1 is 8. So we have a range in our values of 8. The next thing we're going to look at is the median. So this is the middle point. So this is different, potentially different from the mode and the mean. So we're not going to look at the mode and the mean in box plots, but we are going to look at the median, so the middle number. So if you have an odd number of numbers, and so in this case we have 15, so this is what happens. So you add 1, you then divide that number by 2, and that gives you the number that is the median. So in this case, that's the 8th number. So if we count the 8th number, so 1, 2, 3, 4, 5, 6, 7, 8, and in this case it's 6. and we plot that as our median. If you have an even number of numbers, you again add 1 and divide by 2 to get the middle number, and then you take the average of, you'll get a point, usually a 0.5, and you take the average of these, and that would be your median. So it might not always be a full number, depending on what your data set is. So the next thing we need are quartiles. So this is showing a quartile is 25%. So this is a quarter is what we're looking at here. So again, if you've got an odd number of numbers, so in this case we have 15, you add 1, and in this time you divide by 4, and that says how many numbers are in each quartile. So in this case we have 4 numbers in our quartile. If you have an even number of numbers, you don't add the 1. So it would, for example, will be 16 divided by 4, that would tell you 4. If needed, you also average the numbers as we did in the median. So for the quartiles in this case, so our lower quartile, we've got 4 numbers in each, so we count 4 in, so 1, 2, 3, so it's the 4th number, and that shows our lower quartile, or Q1. So we plot that again on our scale. We've got our upper quartile, so we count 4 from the back this time. So you take the last number as the first one, so the last number, and then the next one, so 1, 2, 3, 4, and that gives us 8 as our upper quartile. And again, we can plot that on our plot. Another thing that's important in this is the interquartile range. So that's the difference between the lower quartile and the upper quartile. So in this case, we've got the upper quartile 8, we minus the lower quartile, which is 4, which gives us an interquartile range of 4. So this is the difference between these two. So these are the lines that we've got on our axis. We've got the minimum, the first quartile, the median. It's the halfway point, so you could say it was, it was not Q2 because a quartile is a quarter, but it is the halfway point. We've got Q3, quartile 3, and we've got the maximum. So now what we do is we join all those together. So these are our boxes here. So we join a box from the median to the first quartile and a box from the median to the upper or third quartile. So that's the box part. And I mentioned that box and whisker plots is also how they're known. And these are the whiskers. So from quartile 1 to the minimum, you draw a whisker. And from quartile 3 to the maximum, you draw another whisker. And hopefully this will look now, as you can see, like a box plot. Now in terms of values, 25% or a quarter of the values are within between the minimum and the first quartile. Another 25% are between the first quartile and the median. Another 25% are between the median and the third quartile. And another 25% are between the third quartile and the maximum. I'm just expanding this further. So half your values will be between the median and the minimum value, and half your values will be between the median and the maximum value. So hopefully that is a very simple basic outline of how a box plot is and how it's created and what it means. So now I've got a play along example. So if you've all got a piece of paper there, you can do this along with me. I'm going to give you a little bit of time to basically create a box plot with me. So the data set here is bicycle rides. So I go on 11 bicycle rides, and these are the values in kilometers. So in this box plot, we are going to plot outliers because this is what you'll also see in metagrams. You'll see occasionally some different numbers that are the outliers. So hopefully you've got your piece of paper there. What I'd like you to do first is to sort these numbers into order, so into numerical order. So if it helps, the first number is 1 and the biggest number is 30. I was feeling very energetic on the 30 day to go on a 30-kilometer bike ride. Then I was tired on the second day and just went on a 1-kilometer bike ride. So hopefully some of you are playing along with me here. So first of all, as I mentioned, we have to sort the numbers. So here we're sorting them into numerical order, starting at 1 and finishing with 30. So for those that are playing along, I'll just give you another minute to write down the numbers and check they're in the right order. There are 11 numbers if you're counting. Okay, so the next things to do is to determine the median, the lower quartile, the upper quartile, and the interquartile range. So hopefully you can remember from the previous example how to determine these. The median is the halfway point. The lower quartile is the first quarter. The upper quartile is the last quarter. And the interquartile range is between the upper quartile and the lower quartile. So I'll just give you a minute to do your calculations on here. If you have any questions at any point, as always, please put them in the chat and I'll try and answer them at the same time. Okay. So for the median, we take our number of numbers. So in this case, we have 11 bike rides, so 11 numbers. We add 1, it gives us 12. We divide that by 2, which tells us the median is the 6th number in the sequence. So in this case, the 6th number is 10.1 kilometers, 10.1. So that is our median number. So hopefully you all got that. We plot, again, we have a plot on the right-hand side. So we're going to plot our data. So we have we put, it's around 10, it's 0.1. So it's in the vague area of 10. Now the lower quartile, as before, we add 1 to the number, so 12. This time we divide by 4. And that tells us our quartile is 3. So our third number is for our lower quartile. And in this case, our third number is 9. So again, we plot that. It's quite close this time to our median. And we do the same with the upper quartile. So we already know that our quartile is 3 numbers. In this case, we look at the number of values. I've written the wrong one, it should be 11. Oh no, we plus 1, so it is actually 12. So we take our 12th, we minus 3, so 1, 2, 3. And we get to our upper quartile is 12. So that's our ninth number that we're looking at here. And again, we plot that. Interquartile range, quarter 3 minus quarter 1. That gives us 12 minus 9. So our interquartile range is 3. And that is important for the next step when we're looking at outliers. So now this is a new concept. So this is outliers. So in this example, we're going to define outliers. So an outlier on the lower end is smaller than quartile 1 minus 1.5 times the interquartile range. And on the top side, an upper outlier is when it's bigger than quartile 3 plus 1.5 of the interquartile range. Now, one thing just to bear in mind here is that you should, if you are looking at box plots, there should always be like a key of what the box plot is, and that'll tell you what the outliers are defined as, because it's not always consistent. This is usually how it's defined in maths, but I know some of our metagrams are slightly different, and I'll show examples of those later. But this is just, we're just doing an example here. So in this case, we call it our lower fence. So this is when anything smaller than this is an outlier. So our lower fence here is our quartile 1, which is 9. We minus 1.5 of our interquartile range, which is 3. And that gives us an answer of anything lower than 4.5 is an outlier. Now, what you can see in our sort of numbers is that we have 1, which is lower than 4.5. Therefore, that is a lower outlier. We draw outliers with little circles. In box plots, we don't put them as lines, they are little circles. You can have many of them. In this case, we've got 1, but you can have as many as required. Hopefully you've guessed the upper end of the outliers is called the upper fence. So anything beyond this is an outlier as well. So in this case, we have our upper quartile, or our third quartile is 12. We add 1.5 times the interquartile range, and that gives us an answer of, I haven't done that right, that should be 16.5. I was doing this late last night. My math was pretty bad apparently. So 16.5 would be our upper fence. And we can see here we have an outlier of 30. So this is an upper outlier. And again, we draw it as a little circle. Now we still need our minimum and maximum values. So, in order to finish our box plot. So we kind of ignore the outliers in this case. So our minimum value for our box plot is the minimum value not including outliers. So in this case, it's 7.4. And again, we draw that on our plot. Our maximum value, again, avoiding the outlier, which is 30, is at 15.5. Again, we draw that on our plot. Our range, this is just for information. We don't actually use this information much. But the range is 8.1 because we take the minimum away from the maximum. As before, we draw a box on our data and some whiskers. So we've got boxes between the median and the first quartile, and between the median and the third quartile, and we put whiskers between the maximum and minimum. So this is our completed box plot on the right-hand side here. You can see we've got our nice little box plot, and we've got 2 outliers as well. So again, what does this mean? Well, 25% of values are below the first quartile, and this will always be the case. So anything below the first quartile is 25%. We have 25% of values between the first quartile and the median, another 25% between the median and the third quartile, and we've got 25% of our values between the third quartile and our outlier at this side. So in this case, you can see half of our values are within this quite small range. I think it's between 12 and, I can't remember the numbers. I know 8 and about 12. And again, as last time, we have half our values are below the median and half our values are above the median. You can also look at it the other way around. So below quartile 3 is 75%, with 25% above, and above. And if the values above quartile 1 is 75% of values are above quartile 1. Okay, so you might be saying, right, okay, we've got lots of coloured lines and we've done some maths, basically. I've done some bad maths because I can't add, apparently. But what does this actually have to do with meteorology? Again, bear with me. Hopefully this will make sense. So this is our observation at t plus 0. So we've done our observation. This can be anything. In this case, we're going to pretend it's temperature. We've run our control. We've run our model. This is our control run. So this is our best estimate. So we've got our observation. We then run the model from there going forward. So we're going to go forward 6 hours here. Now for an ensemble, we then do something called parameterization, which means we take our observation and when we move the initial conditions slightly around the observation, just to account for any biases or any errors within that observation. So, and then we run the models from that new point. And this is how we run, how all ensembles work. So you do a small perturbation at the start, and then you run the model again with that perturbation. And because we've done a slight adjustment, that will mean that all the physics, biology, chemistry that are in the atmosphere, all the equations that we do are slightly different. So you'll end up with a slightly different result. So this is one of our ensemble members. We then add as many as needed. So in this case, we've got 1 control and 10 ensemble members. So we're going to have an 11 member ensemble here. So again, this is how all the models are run, but obviously a little bit more complex than this. So this is just a demonstration. So you can see each of our ensembles starts from a slightly different slightly different value. So of whatever this factor may be, in this case temperature. So say this is 10 degrees, then one starts slightly higher, some start slightly lower. We run them forward to T+6, and that gives us a range of what the temperature may be 6 hours ahead. So what we can see here is most of our values are 18 degrees and above. We have one down here, one ensemble member that's saying 10 degrees or 10. This could be wind speed, it could be anything, but we're going to pretend it's temperature. Now, what we can do from these values, as we've just done, is create a new box plot. So what we do is order those values into order. We then look at the median, we calculate the quartiles, we calculate if there are any outliers. In this case, 10 degrees is an outlier because it's well beyond our equation. It'll tell us that this one 10 degrees is an outlier. And then we put together the box plot for the rest of the values. So what we can see here is, so 25% of our values are going to be below the 3rd quartile. And then we're going to have the rest, 25% in each box and 25% above above the 3rd quartile and the maximum value. So this is how we calculate meteograms. They're just a series of box plots. So for each time step, we create a new box plot, basically. As I mentioned before, ECMWF has 51 members. Now imagine if for each time step, all you got was a list of temperature numbers. You have 51 numbers for each time step. You can't process that data. So the box plots are a great way of summarizing that data. So you can visually see what the extremes are and where the temperature is going to be most likely, or whatever wind field you're looking at. So this is a meteogram I got yesterday from Open Charts, and it's for Nairobi. So we can see here we've got total precipitation over 6 hours. We've got an example box plot here. It might look slightly different to the one that we've just been creating, but it has the same elements. Now, the only thing that's slightly different, we've got the median, we've got the upper and lower quartiles. The only thing that's slightly different is we've got the maximum and minimum values are 10%. So therefore, there'll always be some numbers beyond here. So it's showing, so we've got 90% of the values will be below this kind of top line, with 10% of values above, and the same with this. So all that 90% of values will be above this bottom line, with 10% of values below it, as these kind of, I suppose they're more like whiskers. We don't get the out, and then we've got outliers, as you can see here. This 10 is an outlier. It's showing it's going off the chart. So yeah, always just check the key for what you're looking at. But we're going to focus on this one. So this was actually yesterday. So those in Nairobi, we have quite a large, I suppose, box plot. We've got quite a large difference in what the ensembles are saying might be the total precipitation over 6 hours here. So we're going to zoom in on here. And what you can see on the right is that I've created a box plot based on this forecast. So we've got our outlier at 20 millimeters per 6 hours. And hopefully you can now start to see some of the similarities between box plots and meteograms. So as I mentioned, meteograms are just a series of box plots. So here, this line is showing the median. This is the upper quartile, so the 3rd quartile. This line's the lower quartile. We've got our minimum value, which is down here. And these are at 90%. So the calculation here is slightly different, but it kind of, hopefully you can see the same. the lines at the bottom show the ensemble control. So I did mention the control. So that's the member that runs with the best known observations that we have. So it's not perturbed. It's the one that we know we've taken the observation, and that's the start point for that member to run. So we can see the controls down here. We can see the high resolution model is also saying that in this case, precipitation is going to be very low, below probably 0.5 millimeters in 6 hours. However, we do have a member saying 20 millimeters, so they're quite different. So hopefully you can see the how they're so similar. Now I've mentioned just always keep an eye on the key. Now uncertainty. So what we're looking at here is how big our box plot is, or how big is our kind of meteogram. So the smaller the range and in the interquartile range, so the smaller this, the smaller the uncertainty in the forecast. So we can be more confident that that forecast is going to be within those bounds. So if you take, for example, again, we've got a scale on the right. So in this example, seeing this the value is more likely to be within these bounds, so between 8 and 15, than it is if you see a meteogram or a box plot looking like this. So this is showing sorry, go back in, a larger range. So we've got a lot larger range here. So we can be less certain in the forecast because our ensemble members are showing more spread. This is showing our ensemble members are quite close together. There are a couple of outliers that we do need to just keep an eye on and see if it is, because an ensemble, I suppose you could say an ensemble is, every ensemble member is saying it is likely. It's there for a reason. So we do need to just keep an eye on these outliers, but there's a high chance that whatever value you're looking at will be within these bounds. What you will generally see, and I'll show you some examples in a moment, is that the smaller the ranges, the small ranges, so like the one on the right-hand side, is usually closer to that initial time step. And you get the larger ranges with increasing lead time as the uncertainty in the forecast, the members spread out. So you'll see it as the members spread out and lead time increases, you'll see that you get a larger range of data. So we're just going to look at, again, a Nairobi meteogram that I got yesterday. So what we can see here is closer to the time, these little box plots, or these little plots, are very, very close together. So we can be quite certain here. All our ensemble members are showing that the temperature in Nairobi, this was yesterday, so hopefully it was correct, is between 16 and 18 degrees C. So we've got a lot of confidence there. All of the ensemble members are saying this is what the temperature will be. Now, as we get further out in the week, you can see you get a larger range. So a larger interquartile range and also a larger range here. So slightly less certain, but actually in some places you have more certainty than others. So in Africa, for example, with temperature, you generally know what the temperature is going to be. I'll show you an example in a minute from Europe, and you can see the temperature changes ridiculously. Wind speed is generally less certain in general. So here we've only got 2 to 6 meters per second. You won't really feel much of a difference here. Apologies, I've washed out, the sun's come out, so I've my camera seems to have washed out slightly. And you can see you've got quite large ranges here, sometimes slightly smaller ones. So we're looking at those. Now this is a meteogram for Reading, again taken from Open Charts. And what you should be able to see here is you can see you can have a think about what this is telling you. So I mentioned as you get higher uncertainty as you go out in time. So if you look at the 2 meter temperature on the bottom right, you'll see that we've got quite good certainty that the temperature is going to be, especially this morning apparently, it's going to well, let's take midnight. Let's take midnight last night. All the ensemble members agreed the temperature in Reading was going to be about 9 degrees. You've got a very, very small spread in those meteograms. As we run out in time, you'll see that those meteograms, or these little box plots, get bigger and bigger. They get a larger and larger range, showing that the ensembles don't all agree. So some of them are showing we could get up to 10 degrees in Reading. So midnight on Saturday, up to 10 degrees. We could also get freezing conditions. Going further out to middle of next week, we could have, the ensemble members are showing everything between 9 degrees and -6. So that's quite a big spread going on there. As we get closer to that time period, the ensemble members will probably start to kind of gather all to suggest a smaller and smaller range, but we are looking at those ranges. Wind speed, as I've mentioned before, it can be quite large quite early on. We're quite certain here, but again, it gets larger later. Cloud cover, I always see very large spread in cloud cover meteograms. So I think it's just because it's harder to forecast cloud, and you've got so many different levels. Precipitation is one that we're always interested in England. We talk about the weather all the time, and we love our, well, I say we love rain. It happens a lot. We're always very interested in rain. So what we can see here is Friday, we've got quite a large spread. Even our control is suggesting we've got quite a bit of spread, potentially a decent amount of rain on Friday, and we've got again some outliers. So in this case, our outliers are going beyond the top of the graph. We've got one here that's 21. So I believe to create these meteograms and to create the scales, they look at the most likely, and then anything over goes into these numbers at the top. But take the example on Thursday afternoon. We've got one member is saying 21 millimeters of rain in 6 hours. However, the majority, so 75% and below of our ensemble members, are saying we're going to have probably 2.5 millimeters or less. So that's how to interpret these. And I'm just going to finish with extended range. So this is an EFI plot that we showed you yesterday. So we showed you on open charts, if you click on them, you get a meteogram. So this is a plot. I'm going to click just over in, I suppose it's South Sudan and Ethiopia border. There's an area of temperature showing something interesting. There's something going on the border of South Sudan and Ethiopia for temperature. So I'm going to click on that. And this is the meteogram that I get. I've mentioned the key before. Here is the key. So always make sure you kind of understand the key. We've got the climate here shown on the meteogram. We've discussed the model climate this morning. So this is what is expected for this time of year based on model climate. So we can relate that to these kind of shades of red. So this is what the model climate suggests. These are anomaly plots. So what we're seeing here is, compared to what we would expect from Friday onwards, we see higher temperature, over 2 degrees higher than we would expect for this time of year in that area. So that's why it's showing up on the EFI. And as we go out in time, so we get to Monday, the 22nd of February, so these are very extended range, we see that the temperature does start to get towards normal again. We can also see we've got an increase in the spread of these little box plots. So we're seeing that the ensemble members are suggesting that it is going to get closer to the model climate. However, we are still going to probably stay above the model climate for a significant period in this area. And we've got, and if you look at the bottom plot, so the surface temperature plot, we can see here that on Thursday, this box plot is suggesting that all the members of the box plot are saying, actually, we're going to be above 90% of the model climate, what we would expect for this area. So it is going to be over 2 degrees warmer than we would expect for this time of year and going forward. Right, so that's everything on box plots. I can see there is something in the chat, so I'm going to check the chat now. And if you have any questions, please let me know. I hope that is a very short introduction to how meteograms are made and how to interpret them a little bit better. So thank you very much for your attention.
Thank you.
So we've had, can you repeat on the ENS control line? So the control line in the metagrams is, as Anna said, is the red one. So it's one ensemble member. It's run with the best initial status that we can get. So we take, say you look at a temperature, a thermometer, and it says it's 20 degrees. That is the best estimate that you have. It's what your observation says. We then perturb them slightly. So we might run a model starting at 21.1 degrees. We might run a model starting at 19.9 degrees. And there are little perturbations. So they're called perturbations. And that's where we move it slightly to account for any biases. So the thermometer might be slightly calibrated slightly incorrectly. We might have read it slightly wrong. So we're looking at all those little things, and that's why we perturb the models to create our ensemble members. So a question from Paulino: in terms of getting more accurate forecast, which method is the best between taking 51 members and selecting the 10 best performance members and getting an ensemble of them? So it's hard to say what are the best 10 performing members. So it's going to sound really picky. So we could say one member might perform better. We do actually look at if some members are performing better, especially for things like tropical cyclone tracks. We'll look at those. But generally we see that actually we're better taking all the options, because it does give you those extremes. We could take the 10 best performing members, but then we're getting rid of an awful lot of data. And what does best performing mean? I know that might sound strange, but what are we looking at? And how do we know which ones are best performing? Some of them might be best performing for a little bit, and then we get a lot of changes of weather in the UK. We might get then a change of weather type, and that might not be actually the best performing member. So I think the two things that make a forecast better: higher resolution, so smaller boxes over a smaller grid box, because then we can account better for local conditions. The smaller the boxes, the better we can take into account of local topography. So, for example, mountainous regions or valleys, because they've all got different types of weather. And also more ensemble members. You get more of an idea of what's most likely. You'll get the outliers, which is what we see. You do need to take account of those outliers because they are very important to look at. They might disappear, but it's also always worth noting, because it's those events that if they do come off, an ensemble member is saying it's possible. So if there's always it might be 1% possible, but there's still that 1%. So 1 in every 100 times that member may be right. So we always need to kind of keep an eye on those. But for your general forecast, you'll be looking for which, the small, what's most likely. You'll always get those extremes. Sometimes they're called black swan events, especially in climate change. You'll get those extreme events that you can't predict, that we don't know is happening until they're happening or very close to the time. But you kind of always just looking at those, you're looking at the range and the interquartile range really, to give you an idea of what's most likely. So hopefully that's helpful, Paulina. How do you turn the information in the ensemble box plot into probability of an event occurring? Can I get back to you on that one? I'm just going to have a think. Oh, Anna said about Paulino. Yep. 10 best members, complex as they change with time.
Becky,
yes.
for the reply to, let me find. Maureen, yeah, if you just show an EPS, if you just show a meteogram and you just sort of, maybe this one is, one of these where you have a big sort of, so you can just describe the 50% probability of values above or below 30%. I think that's what she means.
Ah, got it. Right. Yeah. Yes.
So if you could just go for one where you have, you can see not the one that is squashed.
Like that one.
Yeah, probably it's better if you get one. Yeah.
Like that one.
Yeah.
Right. Okay. Thanks, Anna. So in terms of probability, so as I mentioned before, so we've got so within this box here, we have 50% probability that this will be, that the value will lie within this box part. Now, for using this key, we can see that we've got 65% probability that the value will lie between this top line and this fat bottom line. And then we've got 80% probability of it lying within this kind of bottom, within this kind of big box area. Hopefully this is making sense. I hope you can see my mouse. So yeah, 80% chance of it lying within this blue area, and then you've got 10% each side of it lying beyond those blue areas. So that's how we can change these into a probability of an event. So as I mentioned, the smaller the range, and so the more squished the box is, that's when we can say the probability of the event is within. We can see some of these are very, very, very small. So we see the probability of the event is actually a lot higher, that it's going to be within these values. So because we know what the median and the quartiles are, that we can turn those into probabilities. Hopefully that makes sense. I apologize if it doesn't. I can try again. Hello?
Yeah, thanks, Becky. I think I've understood. But then the question is, can you turn that into an actual value of probability, rather than just saying, like, we are very confident that this event is going to occur?
I think it's quite hard to do something like that, especially if we take this example. We've got such a range. I suppose knowing the number of ensemble members, so you know, so we know there's 51 in this range, and one of them is saying 20%, so that would be about 2% chance of that one occurring. You can probably do a bit of maths and figure out how many ensemble members it means are within each quartile. So it'd be 12.5 per quartile. So we've got 12.5 members are saying it'll be above whatever that, well, about 7 degrees, and we've got 12.5 members are saying it's going to be going. No, try again. Apologies. So yeah, so 12.5 members are saying it's going to be above, in this case, 3 degrees. 3 millimeters per hour, and we've got 12.5 members are saying it's going to be below 1 millimeters per hour. So I suppose you are just looking at you're looking at how squished it is, so it is really hard to put a probability on it. I don't know if that makes any sense.
Can you just repeat exactly, not Becky, the person who asked the question, can you repeat exactly, because I think the meteogram is actually giving you the probability of the event. So for instance, in this example that Becky has, it will tell you that, wait a minute, on the specific one. So if I look at the 90th percentile, which is between, it's just below 8, so maybe 7, I would say. So this specific meteogram will tell you that you have 10% chance that your precipitation, I think, is above 7 millimeter over 6 hours. Yeah, 10% of an ensemble of 50 is about 1 or 2 members probably. Yeah, but you have 90% probability that actually the precipitation is below 7 millimeter. Yeah. So then obviously it depends on the risk that you can take. Yeah. So you can decide that, okay, I'm happy with the 90% and that's it. If you are a bit more kind of risk averse, you may want to take action even if it's only 10% probability of having the higher rate of precipitation.
Okay, great. Yes, makes sense. Thank you, understood.
So
thanks, Anna.
Yeah, for this one here, for instance, which is, sorry, I'm trying, because here you don't see my pointer, but if you look at the value, say, still in the red box, but you look at the value 3 millimeters, which is the 75 percentile, yeah? So here it means that you have 75% of your members being below 3 millimeters, and the 25% members being above that value. So 25% is a quarter of your ensemble members are actually telling you the precipitation is above 3 millimeters. Yeah, and again, you know, you can decide, okay, am I prepared to take the risk? Am I not prepared to take the risk? But that's a different decision, I guess. Does it make sense?
Yes, it does. Thank you very much. I think that's very useful consideration, especially when we have information on the box plots for us to figure out whether the probability is good enough for us to take action or not. Thanks.
Yeah. Thanks, Anna.
Obviously, if your box plot is it's very squashed and very concentrated in a range of values. So like Becky was showing the one in temperature in Reading, where it was just basically the box plot was all kind of squashed into one. Yeah, that's very easy to forecast, obviously, because you can just basically give one value and you know that more or less your members are going to be all around it. Yeah. So there is a question about high resolution and control forecast. So
yeah, what should be taken as best guess, control or high res?
Yeah, the high resolution is at the moment is the highest resolution model we have at ECMWF. So you expect that obviously the higher resolution would somehow be better than a model that is a lower resolution. This is all fine if you are looking at the start of the forecast, because obviously the uncertainty that we discussed yesterday is the smallest. But as you progress with the forecast, then you may want to think about, having some information about the uncertainty. And this is when the ensemble, which is a slightly lower resolution, comes in. So say if you probably want to do a 6-hour forecast, then you probably would go for a high resolution model. But if you want to do, say, 2 days forecast or so, you may want to consider the uncertainty as well.
Yeah.
So it's not one versus the other, but it's more like, the specific ensemble is actually adding some additional information for you to make decisions.
Yeah. So for example, you can see on this total precipitation plot in Reading, you can see the high resolution going out to mid next week, actually suggesting a lot more rain than the ensembles are saying at the moment. So you've got to take that information all together and say, actually, the high resolution is going for more rain than the ensembles are saying. It's something that we'll keep an eye on going forward.
Yeah. So basically, the ensemble is describing the scenarios which you can't do with with only one model, and this is especially helpful when you're going, higher out into the forecast range. So, if, for instance, in this example of Becky if you look at the total precipitation, if you look at the first 12th of January, you see that everything is relatively squashed and there's not much uncertainty. But as you move away, you will see that the uncertainty is growing. Yeah.
Yep.
So you would, if you just use the high resolution, you may not just, you may not be able to spot scenarios or which are more probable than others.
Yeah. Thank you, Anne. Okay, I'm just going through. Anna's been answering a lot of the questions, so thank you. Oh, great. Cool. So I think that's all the questions that I can see in the chat and comments. Has anyone got any others they'd like to verbally raise? I can't see any hands raised, so I'll say thank you very much. Hopefully that was helpful. Again, I will happily share the presentation with you after this. I believe you've been sent some of the presentations from yesterday already, so I'll share it after the course. Great, thank you very much. So next on the agenda, we have some expert presentations. So I'm going to hand over to, I'm not sure who, there was a couple of options.
Yes, we have a presentation from ICPAC. My colleague Hussein will present, and then if the KMD, we're expecting Chris, I think from KMD, If he is ready, then he can follow up after that.
Great, thank you very much. I'll hand straight over then to Hussein. Thank you.
Thank you. Good morning, everyone.
Good morning.
All right, I'm sharing my slide now.
Perfect, we can see that perfectly.
All right, thank you. So I'll be presenting on the use of ECMWF data and products at ICPAC, which is at regional level. Then Chris from KMD will be presenting on the use of the products at a national level. Before I go on the use of ECMWF data and products, I just want to give a very brief introduction about ICPAC, since some of you are not very aware of it. ICPAC established in 1998 as a drought monitoring center in Nairobi. Then in 2007, there was a protocol to establish the center. Then it was signed and the name changed to IGAD Climate Prediction and Application Center. Currently, ICPAC is a WMO regional climate center for Eastern Africa. ICPAC is also a member of the AUC and the NEPAD network for water centers of excellence. ICPAC also has an observer status with UNFSCC since 2016. So ICPAC is serving the 11 countries in Eastern Africa, the 8 IGAD member states and 3 non-IGAD member states, including Tanzania, Rwanda, and Burundi. So we are serving at 11 countries in East Africa. And our mission is to foster climate service and knowledge to enhance community resilience to climate shocks in the Greater Horn of Africa. In terms of the service, we have a unit of disaster risk management, climate forecasting and early warning, agriculture and food security, environmental monitoring, climate change, hydrology and water resource, and the climate information disseminations. So the core function of ICPAC is the climate forecasting and early warning. And we produce products 10 days and weekly, monthly, and seasonal, including climate extremes. Also, we have the climate monitoring products, and also we do climate prediction and modeling, including research. So if you go to the ICPAC website here, you will get the different products. In terms of the S2S timescale, we use different tools and products on seasonal, monthly, and timescale. We use the global climate model outputs, and we statistically downscale them at a regional level. Then we also run the WRF regional climate model and produce different climate products on shorter time scale, mainly we use it for weekly forecast and to produce rainfall extremes on weekly time scale, as well as to track the tropical cyclone when it occurs over the tropical Indian Ocean. And also at the beginning of the rainfall season, we produce the onset, dry spells, wet spells products for that particular season. In terms of the current use of ECMWF data and products at ICPAC, we use it as input for regional consolidated monthly and seasonal climate. We use it also to assess the current and predicted state of global climate drivers like the ENSO and IOD and those stuffs. And also we use some of the products from the raw model output to assess the climate outlook at a global and continental level. Now, we have also real-time data access of ECMWF data through WISER, W2SIP, and SWIFT projects. So we use that data to produce sub-seasonal climate products, mainly for agriculture, food security sector, and water sectors. And we use also other data from ECMWF, not only the forecast, but like what Roger showed yesterday, this ERA 5 data, we use it for case study analysis to examine the large-scale climate drivers and major circulation mechanisms for that case study analysis. We use also the ECMWF data to assess the skill of the model over the region in comparison with other global prediction systems. So from now on, this I will be showing you some of those products that the data and products that we use at ICPAC. So as I mentioned, we use the ECMWF data for input for the regional consolidated monthly and seasonal climate outlook. So in ICPAC, when we produce the regional and the seasonal, the monthly and seasonal regional climate outlook, we use two different techniques and we use different models. So one of the methods that we use is called the ensemble regression, and the other one is the climate predictability tool, which uses canonical correlation analysis, which most of you are aware of this. So we use this two techniques and we combine them objectively, then we get the final outlook. So ECMWF is one of the models that we used. So currently we are using 10 global climate model outputs for monthly and seasonal climate outlook. So ECMWF, as you can see here, is one of the data that we downscale at a regional level. So we combine all the models from the two techniques, from the ensemble regression and the CPT, then we get the final objectively consolidated climate outlook. So this is how we produce the seasonal outlook. And also we use the ECMWF product. This one, we just use the product, not the data, mainly to monitor the state of global climate drivers. As you can see on the left is the ECMWF, and the right one is the multi-system. So this is it from all the Copernicus multi-model. So we use this product from the C3S web portal. So we look at the prediction on the state of ENSO. We also look at the temperature anomaly and also the sea surface temperature anomaly over the at the global level to look at the major drivers like the ENSO and the IOD. So as you can see here, it shows us there is a La Nina currently over the tropical Pacific Ocean. And also we use the products from the C3S portal at continental and global level, mainly just to compare our products with the signal from the raw model outputs. So we also inspect this kind of products when we produce the regional and seasonal climate outlook. The other product, as I mentioned, is we produce sub-seasonal products, which is products at weekly time scale for the next 1 month. So Massive usually produce this one for food security and nutrition working group. they get these products every 2 weeks. So products like the soil moisture anomaly, and also the weekly maximum temperature anomaly, the rainfall anomaly, and as well as the soil, and also probability of exceedance for those particular areas, and also the area average over a particular country. So this one, we get real-time data through the SWIFT project and W2C project. So this one is mainly for FS and WG work group. Another one is for, again, water and agriculture users. This is mainly for project sites. So Antonio usually produces products and share with those the users, mainly for this for ACRE project. It is a project which is implemented in collaboration with WMO and ICPAC. So this product is shared with the users for those particular project sites. Another one, we use ECMWF data, which mainly the ERA 5 data, which Roger was talking about yesterday on how to access them. So when there is an extreme year, like there is a dry year, there is a wet year. So the main thing is to understand this, the large scale circulation features. What is driving that particular dry year and particular very wet year? So for example, we look at 2018, as you know, March, April, May was very wet, and March, April, May 2019 was dry. This is the precipitation anomaly for different months, for March, for April, and May. Then we look at the large scale feature, what is driving. So this is, for example, it's the sea surface temperature. As you can see, for 2018, March, there was above average SST over the Arabian Sea, but when you look at the 2019, there is a negative sea surface temperature anomaly, but when you look at the SST over southwestern part of the Indian Ocean, it is very warm. So mainly the ITCZ like remains over here, and it leads a delay of the onset for the region. So we do this kind of analysis using the data from ECMWF, including reanalysis and also the forecast. We also assess the skill of those models that we use at ICPAC to produce the monthly and seasonal climate outlook. So this is an example. Again, we use different verification metrics. This is a rock skill score for lower tertile. This is on monthly time scale. This is for March, and the second one is for April. You see most models generally have high skills during March and low skill during April. But so as you can see, ECMWF is one of the models that we assess the skill in the region. And if you look at during March and during April, you can see ECMWF high skill over the region. So it is really one of the skillful models that is available currently. And we are happy for that. And not only on monthly time scale, we also assess the skills on the seasonal time scales. This is another a case for October, November, December. The previous one was the S2S models. These are the models that we use to produce the seasonal climate outlook, which the configuration is slightly different. And again, you will see ECMWF again shows higher skill over the region. So it is again one of the skillful models in our region. What is not available, I just added this slide now. So as the ECMWF data and products are available, but the real-time data is not still accessible. And at ICPAC, we are very much interested to use the ECMWF real-time data, mainly to downscale using WRF model at regional level. So we produce downscale products at ICPAC by running the WRF models. This is an example, the total precipitation on the left and the extremes on the right. So it shows the areas, which areas are expected to receive very high rainfall, extreme heavy rainfall. This is a 99 percentile, this is a 95 percentile, and so on. So it shows the areas that are at risk. Since ECMWF is one of the skillful models, we are really interested to produce this kind of products by downscaling the raw model output. So these products are produced by downscaling the CFS forecast, not ECMWF. So this is just the last point that I wanted to mention. That is all I have. Thank you very much.
That was brilliant. Thank you very much. Really interesting.
If there are any questions, I'm happy to take.
I have some questions.
Yes.
I'm guessing that you're using the S2S data as a research project.
Yes.
Yes, so it's not made available to external people. This is because I guess you have some restriction on the use of our data, right?
Yes, yes. So that one is only, the agreement is for 2 years. So the SWIFT project is, for example, ending this year, December. So we'll be using we will be accessing those data sets until December 2021. And also the products that we produce using these data sets are restricted. So we used only for the particular users. So for SWIFT project, we are sharing the product for FSNW working group.
So what is your plan after December 2021 then? You know, this ECMWF as licenses, so we have prices to data. I mean, there will be eventually there will be open data, but you know, before we get to open data, it will take a little while. So do you have any? What are your plans?
Yeah, for now we are not sure. Maybe my colleagues can add on that one. If ICPAC have MOU is ECMWF, that would be really great to get the ECMWF data. But if not, when the project ends, if there is no extension, then we will be stopping using those products at that time.
So
maybe my colleagues can add on that one.
Somebody has contacted you and you're working on an MOU, or is somebody working on a memorandum of understanding, or?
In fact, under this new project called the Intra-ACP Climate Services, which is funded by the EU. So one of the activities in that project is to have MOU with ECMWF, if possible, if things work.
Yeah, okay.
Hello.
Yes.
Yeah.
Good morning. Good morning.
Or on that note of the MOU, or at least maybe last time when we had the meeting with the major meeting with ECMWF team, including the head of the cabinet, Fabio, if I remember his name correct. Yeah, there was one of the suggestions that maybe we can start with a research project, for example, as an entrance point. And then we see if we can develop that further into a more full collaboration and help them also to to bring it to the attention of the council. That is, there is something of value that is already going on, and it is beneficial to both sides, to ICPAC and to ECMWF. So maybe this could be a potential entrance that we can pursue to continue using this data beyond December of this year, the end of December. So maybe we can try to contact you to arrange another meeting with the forecasting team and with the head of the cabinet, and to see if the continuity could be the research project that they suggested.
So this, what you're interested in longer scale. So you're not so much interested in weather forecast. You're more interested in like monthly to seasonal scales, right? So the downscaling you do is for monthly forecast. It's not for daily forecast.
Okay, ICPAC's mandate is from 1 week to and longer. So we are not much interested like on the short range weather forecast, but we are more interested on accessing the sub-seasonal from 1 week to a season. So the seasonal forecast and the monthly one is available. But we are more interested to get the 6 hourly data starting from today, maybe to 1 month ahead.
Hello, Sam.
Yes.
Yeah, good morning, everyone.
Yes, exactly.
I have a question about decadal forecast. Why now you don't do it?
Mm-hmm. Why we stopped producing the decadal?
Yeah, decadal.
Yeah, the decadal forecast was produced using the WRF model, but now we moved to a slightly shorter time scale from a decadal 10 days to a week. So there is no much difference like between the weekly and the decadal, the 10-day forecast. So since we are currently producing the decadal forecast, that's why we stopped producing the 10-day forecast.
Can I just ask a question? So decadal for me is 10 years, but obviously
not the other one, not
10 days.
10 days. So
10 days.
Okay, great.
DEK, not DCK.
Yeah. Okay. Thank you. That because the user same time ask why they can't get 10 days forecast.
Yeah, I think the weekly forecast still works if you want 10 days, because we are running it like when you run for the weekly forecast, we run it like 14 days and 15 days. So you can still produce the 10-day product if you are interested on that, using the same data.
Yeah, thank you. We like it.
Okay.
Yeah, okay. This is Abu Bakr again. I just wanted to say to Anna that maybe we can come back again and revisit this issue of data and access. Maybe we can discuss it with you guys outside of after the training, so we can see which direction we can go, whether we can get access to be able to run WRF or to have the same access that we have now for the sub-seasonals through the SWIFT project to continue as a research project. So maybe we can discuss this later on.
So if there are no other questions, then Chris from KMD also will give us a very brief presentation on the use of ECMWF data and products at national level.
Brilliant, thank you very much.
Thank you. Chris?
Yeah, good afternoon.
Good afternoon.
Wondering if I can be seen or...
Yeah, we can see your screen. It just needs to go into presentation mode.
Yeah, so I love a lot of products to show, but I love quite a number of products to show. So I think I'll take about 10, 15 minutes.
Yeah, that's no problem. That sounds great. Thank you very much. Yep, that's perfect. I'll leave the floor to you. Thank you.
Yeah, so good afternoon, good morning, here from Nairobi. My name is Chris. I'm with the Kenya Meteorological Department, a climate scientist there. And even here within this Zoom, I have my colleagues, Jemima and Saumu and others. And of course, KMD, we've been using ECMWF products for a long time. We do a lot of forecast, starting from nowcasting to medium range to extended range and long range charts, which, as we all know, have been made easily available recently. And we look at temperature, wind, precipitation, ocean waves, because we also have a coastal line here in the coast in Mombasa and the coastal strip generally. KMD, of course, we supplement all our forecasts with most products globally. And one of them, of course, like I mentioned, is ECMWF. So a number of products that we produce include the severe weather forecast. With this, you know, KMD is the RSMC for Nairobi, for East Africa, the Regional Specialized Meteorological Center, where we are able to look at extreme events, which are very likely in the coming 5 days. The period is between 1 to 5 days. So every day at 12 o'clock, we have a severe weather conference for the whole of East Africa. And my colleagues who always attend this conference, we have Ezekiel from Burundi and others. They are also here. Of course, these guidance products are based on a skillful evaluation of both regional and global models. And we have our WAF products, which we also run. We look at the satellite imagery to try and see, to get verification for the forecast that we've issued. And we look at a lot of things, including the local features. So the criteria, of course, is 50 millimeters and above for rainfall within 24 hours. We classify that as quite severe. Of course, the classification is that anything that is between 5 and 20 is moderate. Anything after 20 millimeters is heavy. But still, when we have severe events where we could have more than 50 millimeters of rainfall, we classify that as severe. We also look at wind speeds, especially for the northern parts of the country, where we've got wind turbines, and parts of the coastal region, where we could have potential strong waves because of the strong winds. We look at the wave heights, and all of these products, the ECMWF products, are really help us. So these are sample products of what we usually have, and like you see, these are the product that was issued yesterday, and you can see parts of Tanzania. We expected more than 50 millimeters of rainfall within 24 hours, especially the coastal region. These towards central, southern Tanzania, southeastern Tanzania. We also expected strong waves of up to more than 2 meters, and parts of the northern parts of the country, these towards the northwest, and parts of southeastern Ethiopia. Yesterday we expected some strong winds of more than 25 knots. So these are some of the products that we normally have. So you can see this from ECMWF. But here in East Africa, because KMD is specialized, we have a specific link especially for severe weather demonstration projects for East Africa, which KMD has got a password. So we've got a smaller domain for Eastern Africa, and these are the products, 6 hourly products, and you can see this for day 1. And we also have a probability of exceeding 50 millimeters. So again, these are very important products. And as you can see, where we had noted, just going back to the previous image, we had noted about 50 millimeters or more in southeastern Tanzania. And when you look at the warning, the probability of exceeding 50 millimeters, again, this was captured in this product. So it's quite useful whenever we are doing the severe weather focus. And as many of you have mentioned since yesterday, we have the EFI. Of course, the EFI is something that exceeds what we usually expect, exceeds the normal, something quite unusual. So as you can see, for day 1, again, as we had issued in the forecast that was given yesterday, again, day 1, we can see something that is approaching 1, which means that the extreme forecast index was quite okay. So we'll have the verification later on today after the conference, which probably my colleague now is at that conference. She's called Saumu. And most of these products, you can see they're quite reliable. And we've always had a table where we are able to see whether we usually verify these products, and most of the time the scale for the EFI is always quite okay. We are also looking at wind, and for the coming number of days, for day 1 up to day 5. And of course, we use ECMWF and other products, including the GFS and the Met Office products, which again, we've got special access. And these are the sample advisories. So the last advisories that we issued, the last advisory rather that we issued was in November last year. And we expected rainfall over several parts of the country, especially the southern and the western parts of the country, and parts of the coastal region. So most of these advisories again are informed, especially by the EFI and other products. I mentioned about the waves, and we've also talked about the box and whisker products. And from this, you can see we are able to note whether we are likely to see waves which exceed 2 meters. And because of that, it can be tragic, especially for fishermen at the coastal region. So this for 2 islands, Mombasa Island and Pate Island in the Kenyan coast. So most of these products, again, we normally rely on the ECMWF data. So this for Tanzania, we just don't look at Kenya, because RSMC Nairobi is for the whole of Eastern Africa. So these are the sample products. So we are looking also at the coastal regions of Tanzania. So apart from the severe weather forecast, we have the weekly forecast. And my colleague who is with us in this meeting, she's called Jemima. Also, she was working on this, and most of these products that we use, of course, some of them from ECMWF, inform our forecast. So especially now, when we look at the rain and mean sea level temperature, when you go into the website for ECMWF, you can click at a point and be able to get the box and whisker plots, and you can be able to look at the total precipitation as explained earlier, the upper quarters and the lower quarters. And I think everybody may have listened to that. So quite very helpful. We, like Hussein said, our colleague from ICPAC, of course, KMD, of course, has got the sub-seasonal to seasonal products. And we use a lot of that. And through the SWIFT program, we are able to access some products. These are the ones that we especially used during the January forecast. The S2S is very important for us, especially nowadays when our users have always requested for weekly kind of forecasts within the monthly forecast. So when you look at our monthly forecast, nowadays we are able to talk about how the first week of the month is likely to perform. Like when you look at this monthly forecast that was issued for January, the Lake Victoria Basin and mainly the western parts of the country, when you read through bullet 2.2.1, these regions are likely to experience generally dry conditions for most of the month. However, occasional to light to moderate rainfall is likely during the first week. And that was greatly informed by some of the products that was the run that we had before the beginning of the year 2021. So we also look at the temperature, and we can be able to look at the performance on weekly basis. So a lot of products that we develop from ECMWF data. So from that, of course, from the website, again, you can get the seasonal forecast. Like this one is what we expect for the coming season. Quite normal conditions, but of course, this using the initial conditions for probably in December. So of course, most of this usually change as we near the season. Apart from that, as we know, the MAM forecasting in most of East Africa is quite complicated, and therefore we look at MJO and other global drivers. And as you can see, the faces here for MJO are quite varied for the Glossify, for the CHAPS, and ECMWF4. So through some other project called the 4PAC project, we are able to access some of this information that really helps us whenever we want to know the kind of phase that we are in with when you look at the MJO and how it's going to affect our weather in Eastern Africa. So of course, through again the WMO site, we can be able to get ECMWF data, ECMWF forecast rather, and you can see it's a combination. These are just an ensemble. So when you also look at the seasonal forecast, normally the onset of the rains has been quite a challenge, especially for MAM season, March, April, and May, and OND. So normally with the beginning of the issuance of this weekly precipitation anomalies, we've been able to try and see when we are likely to see the onsets. So when you look at the onset that was issued for OND 2020 rains, we were able to not just look at the normal statistical years, the analog years that we normally identified, like that was for the last season, we had identified 1995, 98, and 2016, which were quite dry. And normally what we would do for us to identify the onset of this season, we would look at the data, the statistics, and see when in 1995, what time of the year did we start receiving rainfall in October. And with that, we would be able to identify when we are likely to have the onset. But now, since the beginning of OND 2019, when we had quite significant amounts of rainfall in Kenya, and most of East Africa, given the positive IOD. We were able to precisely identify when we were likely to have the onset of the season. And that was especially when we had the SWIFT project, which provided us the data to run the weekly anomalies. And with that, we were able to be quite accurate in our forecasts for the onsets. Apart from that, we usually provide supplementary forecasts for our users. Now, like this one is for OND 2020. And one of our users, the Red Cross, is among us here, Maureen, from KRCS. And of course, we have Kengen. So these are just sample products, which are also, we incorporate ECMWF data. Of course, we welcome SKMD, the use of ECMWF data, which was made free and open, though there are some special products which are given to KMD. KMD are subscribed and possibly pay for the same. But we welcome the idea that the data is now free and open. So that's all. But I have a number of products I would have liked to show, but maybe I'll post them in the chat. That's all. Thank you. Thank you for having me.
That was great. Thank you very much, Chris. Really, really interesting. It's great to see how much ECMWF data is used. Has anyone got any questions for Chris?
This is Anna. I just wanted to say that, yes, unfortunately, I had some issue with the internet again. I think 9:30 UK time is a problem for my internet. So I missed some of your presentations, but I think it's, I've seen part of it and it looks like you're using a lot of ECMWF products. So the question will be probably, is it maps or data itself that is more valuable to you? Is that maps of already produced, or is the actually underlying data that are more valuable?
I think for KMD, both would work, especially now that when we develop the sub-seasonal products, we have to have the data where we use Python and the scripts which we've developed whilst we were in Reading. So I think it has been, we use both SKMD. Of course, the charts are also available on the website. Yeah.
Mm-hmm. You're aware of the fact that seasonal forecast can be retrieved from the climate data store?
Yeah, I'm sure we can always access the same, the ECMWF data. We usually have, we work with ICPAC whenever we are doing this seasonal forecasts. We always have to retrieve some data so that we can plot the graphs.
Great, thank you. Got a question from Can Tamla. He's raised their hand. Oh, no.
Hello.
Oh, hello.
Okay, sorry, I just want to confirm the amount of precipitation that has been observed today following the warning that was issued by the RSMC Nairobi yesterday, especially of the southern part of Tanzania, I mean of Mtwara region. So for today, we have received a report of 139 millimeter of rainfall in 24 hours, which is severe. So I just wanted to show how useful the ECMWF model product, the way how they are useful, and also from 0600 today to 0900 it's still raining over the area, and we have a report of 125 millimeters of rain. just over the 3 hours. So we are still monitoring to see what are the severe impacts that are going to happen over the area. So thank you very much.
Wow, that is a lot of rain. I hope everyone's okay, because obviously that is very severe weather. So thank you very much for the feedback on the forecast. It's great to hear that we can help with events like that. Has anyone got any further comments or questions about anything that we've discussed this morning in this early session? If not, we'll go to a break. So I can't see any hands raised or any further comments on the chat. So what I think we're going to do now is we're going to go to a break for, let's do 20 minutes. So we'll have so 10 past the hour. So it's 9:50 UTC in the UK, in the UTC. So that 10 past 10 UTC. So that'd be 10 past 1 East Africa time. So if we come back then, and we'll carry on, we're going to go more into detail on EFI and cumulative distribution functions after the break. So have a good break, and I'll see you back in 20 minutes. Thank you. So hello everyone, welcome back. Hopefully you've had a nice break, managed to get a drink or something to eat. So this for the rest of the session, so this is for the next about approximately hour and 45 minutes, hour and 45 minutes for the course, but probably just under that for this. We're going to be looking in more detail at the Extreme Forecast Index, or the EFI, and cumulative distribution functions, which are really key to understand how the EFI is created and what it means. So Anna is going to be running the session. Towards the end, we're going to be breaking out into two groups. One, I'll lead one and Anna will lead the other. And we'll go through a few things with you there, and it's that time to ask as many any questions that you have, and then we'll come back at the end. We have a short feedback session where we're going to ask you just for a bit of feedback about the last couple of days and how you found it, and then we'll close after that. So with that, I'll hand over to Anna.
Hi, so I had to change location in the house to try to see whether my internet is any better.
Fingers crossed.
Fingers crossed. So Becky has a presentation anyway, so in case I sort of fail, so she can carry on. So I just want to make sure that it's, I'm guessing everybody is around. So because I'm now going back to the slide, to the, wait. Let's see if I can see it. I'm going to show this one, the website. Is that what I see now, right?
Yeah, we can see it. We can't see. Oh, that's better. Yep.
Yeah.
Yep, we can see.
Okay. So this is one of the initial question was about this plot, the meaning of the two panels. So I just want to clarify a little bit what they actually show. So on this side you have we see the EFI. Yeah. So there will be areas in Africa specifically where the EFI is particularly high, like in this little dot here, in this area here, and this area here. But what is interesting to see is that because we said the EFI is the difference between the climate, obviously you need to know what exactly the climate for the area is. So because we said we are looking at the EFI, so we are looking actually at severe event. So the quantile of the climate that you should be looking at is not this one, which is the first quantile, but is actually a higher quantile. So say you would be looking at the quantile number 90 or the 99 quantile. Yeah, and that will give you a lot better understanding of what you might expect in terms of, well, in this specific case is precipitation amounts. So in this area here, for instance, you have this EFI seems to be signaling something, and the precipitation in this area is of the order of, I would say 2 to 5 millimeters in whatever the period is covered by this one, which is probably a 24-hour period or a day, 24-hour period. So if we go to the 99th percentile or quantile, so you see again, this is the signal. So the precipitation then here, it's of the more extreme cases in the climate is actually of the order of 5-10 millimeters. Okay, so it's no point in looking at the precipitation for the EFI and looking at the quantile 1 of the climate, because the quantile 1 of the climate would probably be, you know, very close to the standard climate that you would expect in the area. Okay, specifically in Africa, I would say, because you obviously have a lot of very little precipitation, especially in this area here. So I hope this is a little bit clear. And maybe at the end of the session, when we are in groups, we could actually attempt to look at the situation, maybe one of these maps, where the EFI is a bit more sort of evident. Maybe we could have a look at Europe, say. Okay, so you see in Europe, there are some very strong signals at the moment. So this is this area, etc. So maybe we could, in the groups activity, we can then look at this situation and then see how we can use the quantiles of the climate. Okay, so that's for it. Now, if I go back to my presentation and I share, hopefully I have it somewhere. Yep. Okay. So this is now, if we start from the start. Here we are. Okay. So what I'm going to do, I'm going to start from the cumulative distribution function. So we are going to have a look how we build it, step 1 to step 4. I think I've got 4 steps. Then we look at how the EFI is calculated once we have built the cumulative distribution functions. Then we're looking at one specific plot of the cumulative distribution function, and we try to deduce some information, and then we hopefully split in groups, and then Becky has the presentation. So one of the tasks of the groups is actually to build a cumulative distribution function. We come back to all together. We share in the 2 cumulative distribution function, what they look like. The one in group 1 and the one in group 2, and then we do a few more sort of exercises on the EFI. Okay, so next one. So this is what I actually used yesterday already to describe the cumulative distribution function and to work on the EFI. And as you remember, we said the EFI is the difference between the distribution of the climate, which is the one in black, and the distribution of the current today forecast, which is the one in red. Okay, so also now I think we are clear that for one specific time step in one specific location, we just do not have, we do not have only one value, but we have a number of values, and this number of values will depend on the size of the ensemble. So if you get the forecast from ECMWF, we obviously will have 50 plus 1, 51 members. In this specific example here, we only have 10 because I didn't want to write 50 numbers. So I could not invent 50 numbers on the top of my head. So these are my values. So assume these values are precipitation values over 6 hours. So we have 15, we have a 0, we have a 7. So we have 10 members of 10 forecasts, and they give us, for one specific time step, one specific location, they give us 10 values. Okay. The first thing we do, we put them in order from the smallest to the biggest. So you have your values here, and now I've ordered them. Yeah. So you see that now the 0 is the first, the 7 is the second, the 9s, and so on and so forth. Yeah. Then we rank them from the smallest to the biggest. So in this specific case, because we have 10 values, we will have 10 rank. Yeah. So the first rank is 0. 0 is rank 1. So it's the first in our list. 7 is the second in our list, and so on and so forth, until number 25, the value 25, which is our number 10. Okay. Then what we do here is we just graph them, put them on the graph. So the graph will have on the y-axis, we'll have the rank, so the position of our number in the series. And the bottom one will have the parameter values, which in our case is the precipitation. So we won't have negative precipitation, so we will start it from number 0. Yeah. So the first value, rank 1, is 0, so we put it right at the bottom. Okay. Then the second value is number 7, and we put it on the second rank 2. The third value is 10, and we will put it on rank 3, on the position 3 in the y-axis. Then we have number 11, then we have number 12, number 13, and so on and so forth. Yeah. So in this way, we have built out of our initial series of values of precipitation, we have transformed them into an ordered series, which goes from the smallest to the biggest. Each value of precipitation was assigned a rank, I mean a position, from on the graph, from obviously position 1 to position 10, because that's the size of our series, and then we graph them. Okay, so, and you do exactly the same exercise with your climate. Now you will see immediately here that there is a little problem because the climate is actually going negative. So obviously this is not going to be a very good example for precipitation, but for the time being, we forget about the fact that it goes negative. Yeah. So now the question is, how do you transform this rank of this rank on the y-axis into some kind of form of probability, because that's what you are interested in. Okay, so we go to the next exercise. We have again our values at the top. These are all our ordered values. And now our step 4 is actually transform the rank, i.e. the position on the y-axis, into percentages. Okay, so our first value was 0. 0 was given rank 1. 1 is 1 of 10. So 0.1, so 1%. Yeah. The 7 is rank 2, so it's 2 out of 10. And this is 2%, and so forth, until we get to 25, our value 25, which is rank 10. So it's 10 out of 10, and this is 100%. So if I now do this, okay, we actually have probabilities on this y-axis as opposed to rank. Okay, so now we have this one. So what does it mean now on this what is the meaning of our sort of cumulative distribution function? So the meaning of our distribution function, we said the second value, which is number 7, which was rank 2, now it's 2%. Okay, so it means that we have 2% probability of our precipitation to be below the value of 7. So 2% is this bit. Yeah, so all the values below 7 have 2% probability of being there.
Can I just clarify, Anna? Sorry. Do you mean 2% or 20%?
Ah, sorry. Yes, 20%. Yeah, sorry.
I have written it in the chat, but yeah. So Anna means 10% and 20%.
Yes, sorry. It's again. I'm sorry. I can't do the math. Can't do the math. Yes, it's 10%. The first number is 10%, and the second number is 20%. Let's correct it because before we meet. Okay. So if I go escape a second. This morning is also, I prepared the exercise yesterday, so it's a bit okay. So this is 10%, this is 20%, and that's correct, no? And the last one is 100%.
That makes more sense to me.
Yeah. Okay, so now we save it. And am I still sharing?
No, you're not.
Okay. Play from present slide. But now
you need to share screen again.
Yes, sorry. I need to share the screen first.
We can see that now.
Okay, now we can play from the current slide. Okay, so rewind. So 0.1 is 10%, 0.2 is 20%, and so on and so forth. Yeah. So now if I uncover this one, yeah. So now we have our axis, and we can say our axis is the axis where showing the probability of not exceeding a threshold. Okay, so if we go back to our number 7, which is on rank 2, that is 20% probability. So we'll have 20% probability of being between below being below 7, or you have 80% probability of not exceeding the values of 7. Is that right? So we have 20% probability of being below the number, the values ranked on the rank 2, which is our 7, and 80% probability of not exceeding the threshold of 7. So all this is 80%. Yeah. So if we go on and we do this one, which is, so this is rank 6, so it would be 60%. So and it's like, what value is this? Probably 13. Okay, so for this specific values, we'll have 60% probability of being below the value of 13. Below, or 40% probability of not exceeding the value of 13, which is that part. Is that more or less clear? This is the rather complicated bit of information that needs to be understood, I think, to be able to read a cumulative distribution function. Is it more or less clear? So if I escape,
I have no comments in the chat at the moment. So
now stop sharing.
Yes, you have.
Yeah.
Hello?
Again?
No, I'm in. Yep. Please go ahead.
Yeah, so people are, oh,
continue on.
Okay, so maybe then I just carry on. So if I carry on in sharing. Okay, so if I carry on in sharing the things from this slide and I go forward. So we've done this one. So we now understand that we go from our values to an ordered time series to the rank, and then from the rank to the probability. And this one is basically information about whether we are below a certain value or we are not exceeding a threshold. Yeah. So if you are looking at the probability of not exceeding a threshold, you will be looking at this value here on this side. If you are looking at the probability of not exceeding the threshold, then you will be looking at this much wider probability. Yeah, so if you imagine here, instead of 0, 1, you get 0, 100. Yeah, and then this one here, it will be your whatever, 60% probably, and so on and so forth. Okay, we can do some exercise on this at a later stage. I think the next one is the way of calculating the EFI. Okay, so now we go back, if we go back to this one, so you have the black line and you have the red line, and here again, you have a black line and a red line. So if you imagine your black line to be your climate and the red line to be your current forecast, yeah, which we said as a number of values for one location in one time series. So the EFI, which is on this formula at the top, and don't worry too much about the formula, it's just basically giving you information about the distance between this curve and this curve. So it's basically calculating the area between these two curves. Yeah. So if the area is 1, that means that this curve here is actually moved towards this side. If the EFI is is very small, that means this curve, the red curve, is very close to the black curve. Yeah, so the area between the two is actually very small. Yeah, and this one is basically just a way of calculating the area. And the top, you have basically the difference between the climate and between these two lines. And underneath here is just something that helps us to normalize the EFI. Yeah, again, here you are seeing that this is the probability of not to exceed a threshold. So if I go here, say 70%, and if I draw a line here, so I've got 70% probability of not exceeding, 70% probability of not exceeding the value of 23. Yeah. And obviously you have the reverse probability, which is 30% probability of exceeding the value of 23. So above this one, you still have a few values that are more than 23. And this is actually 30% of those values are exceeding the value of 23. Okay, so this is a probability of not exceeding a threshold. So if you have 30% probability of not exceeding a threshold, and the threshold is the value 22.5, but you still have a 70% probability of exceeding that threshold. So you have 70% of your values being above 22.5. I hope this is more or less clear. So the idea is that because you on the maps, you tend to see just a color scheme, which is an index, and you want to associate basically that index to some kind of values, which then you can relate to your thresholds, because you are defining severe weather events with thresholds in your specific place, specific location or National Met Service. So you want to look at the map showing the signal of the EFI, the yellow, red colors, but you also want to see what it means in terms of real values of the parameter. Is this make sense? Does this make sense so far? Do I have any questions or?
There are no questions in the chat at the moment.
I understand it's a little bit complicated, but it's really, you know, in a sense, it's really essential that this is kind of understood, because simply because you want to relate a EFI to some real values of parameters, which you can use into your forecasts. Okay, so if we go now next to the next slide, which is a little bit of an introduction to the SOT, which is somebody has requested, which is a shift of tail. I have to explain you why we actually need this additional sort of parameter, this additional product, to give you some more information about how extreme an event might be. So if we're looking at the first plot here, you have the usual climate and you have your usual red line, okay? And you have also blue line here, which is yet another forecast. So effectively, both if we are going to calculate the EFI of the blue line, of the blue forecast, which is the first curve you see on the top panel, and when I find my pointer, I can show you this one. And when you calculate the EFI of your second forecast, which is the one in the red curve, the EFI is exactly identical. So the EFI is always 1. And this is because the EFI is designed so that actually calculates the area between the two curves, but it can't go further than this specific value. this is the more extreme value in our distribution, in our climate distribution. Yeah, so effectively, these two forecasts, they will still have the same value of the EFI, but you can see that the red curve is actually more extreme than the blue curve. So what we've done, we have introduced a specific variable, which is the shift of tail, which measure the distance between the climate and the 99 percentile, so the extreme point in the climate distribution. So just looking at this difference, which is basically this one here. Yeah. And the difference between the same quantile, but for the forecast. So from this curve here to this curve, or from this curve to this curve. Now, if the SOT, so obviously the SOT, then we compare this one with this distance, and we compare this one and with this distance. Obviously, you can imagine that, actually, this is a question. So what do you think it would be larger if we compare this number with this, or we compare this number with the red curve? So which one do you think is the largest? Any idea?
Feel free to put what you think in the chat, or open your mic and just say which one, blue or red.
So if I escape on this one, I may be able to see a little bit more of the people. Any idea? There's no way that I can see the chat in this. Oh yeah, here we are. Fine.
Yeah, it's at the top, and then it pops out. So there's nothing in the chat at the moment. So I think red. I'm not 100% sure.
Yeah. So is it the fact that nobody puts anything on the chat, is that because it's rather complicated, or do we need to explain more? Or it is the red, yes. And this is because the red is much more, the forecast described by the red curve is actually much more extreme than the forecast described by the blue curve. Is it, can I just have, I'm going to stop here now. Stop sharing. Can I just ask people whether they are with us or not? I'm a little bit concerned that maybe we've lost them.
Yeah, so the question is, do you think you understand the EFI, or would you like Anna to go through it in a bit more detail?
Yeah, I would really like to encourage the participants. I think many of them are here, but I would like to encourage them not to be shy and make it interactive. I think we can make the best out of it. It's a very great opportunity, and I'm really enjoying and learning. So yeah, please come forward, and if you have question or comment, or just go forward. It's a very relaxed environment. There's no judgment or anything like that. We're all here to learn.
Well, I mean, one possibility is that I have a little exercise, so we can just work in a couple of groups. So if you see here, for instance,
share. You need to share again.
Let me show this one without going into presentation mode. Okay, so here I have a little exercise. Can you see it? And I'm not going to show in presentation mode, but what I was planning to do is that perhaps this is the right time to go in 2 groups, and then each group will have to come up with the plots. I mean, on a piece of paper, we just show it like this, of what is this, what is the CDF in this specific case. How about that?
Yeah, I think if we go into that and if we can build a CDF and then between the groups, so I'll lead one, Anna will lead the other, and we try and understand I think it's more transforming the rank into probability, maybe that's potentially something that we need to discuss a bit more and try and understand. Someone says that they can understand the EFI and the CDF, but they're waiting to understand the shift of tails more.
Okay, so let's
maybe if I may suggest, maybe Anna can finish her presentation on that part, and then we can go to the group.
Yep, sounds good to me.
I mean, it's fine, but it's the presentation was, so after this one I have one example, which is exactly what we just discussed so far, and then it's a couple of examples, so it's probably a good time to go into the groups, yeah, and try to build the CDF, yeah, and then we come back together, both groups will show the CDF. And then we just go from there and we start again with maybe the SOT and some more examples, so some more interpretation. Yeah?
Okay.
Yeah. Okay. So Becky, you have the slides.
Yep, I do.
Yeah. So we can do the step 1, step 2 on the slide, and then step 3 on the piece of paper.
Cool. Yep, sounds good. Okay, so I'm just going to randomly assign, there's going to be 2 groups. I'm going to randomly assign people to a group and try and make sure me and Anna are in separate ones. And then we'll continue the discussion, and please ask as many questions as you have within these groups, or if we can't answer them, when we come back, we'll answer them as a bigger group. So I'm going to start the breakout rooms now. So please join the breakout group when you get the message on screen. And then when we've finished, we'll come back. When you finish, come back to the main room as your big group, so we know when to stop. Okay.
Oh, it looks like we have, some of us have made it. While we wait, is there anybody of you that actually has, some of you yesterday showed that they've used in the EFI. Is this so far it's been useful, or it was too complicated?
Sorry, can I ask you one question, please? Just for a
Sure,
moment.
yeah, for this reason.
Yeah. The only problem that I think I'm still confusing is when you're using the EFI, especially the spatial map. So it gives you like contours with the scales. Maybe it's ranging from 0 to positive something. So my question is, so how am I going to relate now this spatial map and the cumulative distribution function? So how am I going to put them together to
oh, okay. So when you okay, so this is when you look at the EFI map. Let's see if I have something. I think on my browser I had something already. Let me check. I want to quit the cell. Cancel. Where's my browser? I've lost my browser. Oh, here we are. Okay, so if I now share my browser. Okay, so this one is the example I was going to try to make before. So you see here, yeah, this area here is the area where you have the EFI is quite large. I mean, this is Europe, but it doesn't matter. It could be something. You can imagine this one happening in Africa. Now, on a standard map, not the free ones, you would actually be able to click on it and produce a CDF immediately. In the situation of the open map, you need to go and find it somewhere else, but I'll show you where to find it. So here, what is happening? You actually have a signal of the EFI very high, very large. So it means that the CDF of the climate and the CDF of the forecast are very distant. Yeah.
Yes.
Yes. So this is where actually you get the connection between the EFI, I mean the map here, and the distribution. So like if you can imagine, so when you see something like this, your brain will say, okay, now I can picture the CDF of the climate and the CDF of my forecast to be very distant. This is where the connection is. In a minute, when everybody's in, probably I'm going to show you how you can actually get the CDF from the CDF plot itself. At the moment, so if you are from one of the SWFDP countries, you can actually click on it and probably obtain it. In this setting of the open chart, we have to find the CDF plots in another map. Does it answer your question?
Yes, it has.
Okay, great. Okay, so I think Becky's here.
Yeah, we're all back.
Okay, so how we did with the plot? We struggled a little bit with the plot, but eventually we decided that Excel was the best.
Oh, did you? So I did it on. So I kind of talked everyone through and encouraged them to draw it with me. So I will share what we made. What I made. I had a great time plotting a plot. So we ranked everything all 1 to 20, and then plotted it on our plot to create our cumulative distribution function of 20. I think there's 20 values. towards the top, I think I gave up with counting the dots.
Aha, so we did it like this, and we can show you, we did the same. So we did the step 1, step 2, step 3, and then let me just share my presentation, which is hopefully somewhere available.
Yeah, we also discussed the percentages and kind of turning those into days as well. So 10% means one in 10 days if you were going to turn it. So a different way to communicate those things.
Okay, so we didn't do that part.
It's just a bit of my background, isn't it, talking about the weather.
Okay, so our plot is like this. It's absolutely perfect because Excel did it.
I see. Ours isn't as perfect, but it shows the curve.
Okay, slideshow from current slide. So we did this from the smallest to the highest, and we did the ranking, which is up underneath. It's all squashed up, but each number is supposed to be ranked. And then we did the ranking, but we just a few. And then here we pointed out a few of the ranking that we were interested in. So we looked at 10%, 40%, 100%.
Brilliant.
And we discussed about the fact that on this axis, you have the probability of not exceeding a threshold. Yeah. So this one is the 10% of not exceeding, sorry, the 40% was our 10. So it's a 40% probability of not exceeding the value of 10. And then we looked at the rest of the distribution, which is exceeding the value of 10. And that is the 60% of the distribution. Yeah. And the importance of understanding the CDF, because that one is the things that brings from the EFI map to the cumulative distribution function to the threshold that people are actually using.
Yeah.
Yeah. So I think
we also discussed, which you're probably showing the examples about how vertical the line is, being how much the ensembles are agreeing with each other.
Yes, so we didn't do that yet. Yeah. Okay, so far so good. So I think can you just tell me how much time I've still got, just to have an idea?
About half an hour.
Okay, so because again, I would like to have some more discussion on the rest of the presentation. So if I go off, I don't want to do that. I wanted to start from here. So this one is, okay, so this one is maybe then your group can say something about how verticals they are. So obviously now, this is now an example of a cumulative distribution function for the wind gust, yeah? So on this side, you have the CDF, on this side is just a summary of the values of the EFI. So this is what you will see on your map. The top one will be probably orange, and then it goes into a different color. So the colors here indicate the time ranges. Yeah. So this is the longest time range, and this is the shortest time range. So red is not because it's more serious, but simply because it's the closest forecast. And this is your CDF for the specific variables. And you can see here they've been graphing the various forecasts. So the red one is the latest, but then you also have previous forecast ranges. And here you have a line, which is your whatever 45. No, that's not 45%. Oh yeah, probably 45%.
No, so it's 55% line, and it's 45% chance of exceedance and 55% below.
Oh, okay, 55. Yeah, sorry. All right, 55. 55% of not exceeding, yeah, 18, and 45% of exceeding. So 45% of the members are above this, and you can see them here, and 55% of the members are below 18. Yeah, this is the line that defines the 18 meters per second. So 55 members are on that side and 45 members are on that side. Okay, there are a couple of considerations here. Is that okay? Somebody's switching on the Is the mic, is it?
Yeah, it was Mohammed, but I think he switched it off again.
Yeah. Okay, so this is now, there are some consideration here to make on this one. First of all, it's the fact that you can see the forecast ranges, so the different colors line, they're all kind of very close to each other. They are not spread around. Yeah. So that means that the ensemble, even from the more distant time step, from the further away forecast, is actually being forecasting some kind of potential severe event in the area, this specific location. Yeah. And you can see this, the same message, you can see it on this side, because you can see the value of the EFI is very similar. So it's about 68 and it goes up to 73. Yeah. So if this one can be, this one, you can see it also in terms of from 0 to 1. So that would be 0.6, yeah, to about 0.7. So it's very much in line. So that means that the ensemble has been consistently forecasting a potential severe event in the area. Yeah. Now, I think Becky, in your group, you have discussed about the fact that the lines are more or less vertical. So maybe somebody in your group or yourself want to say something about it? It's just because I don't want to speak all the time myself, because otherwise it's a bit boring.
Does anyone in my group, in group 2, want to give an overview of what it means when the lines are more vertical than others? People are a bit shy. So I can't see anyone. So
I can volunteer.
Ah, perfect.
I found my colleagues are a bit shy in the group, so I thought, yeah, the lines, as I understood, as long as it is it's steep, so that means most of the members are in a kind of agreement. So the variation, for example, in the parameter, whether it's temperature or wind, between the or the range of variation is more smaller. So this is regarding how steep the line or not steep, and of course the distance between the from the climate and the forecast, it gives more area, and as large as the area between the two curve, the larger is the EFI, which indicate that the severe event is more likely, if I get that right.
Yeah, so that's correct. So the distance from this forecast and the red one, we just use itself, it will be the EFI, and you see in this case we have values of 0.7 or 73%, whatever, and how sort of bent the curve are, or not bent the curve are, will give you the range of values that are predicted by the ensemble. So you understand that if the curves are more straight along, then obviously the range of values here will be quite small compared to curves that are like the climate. For instance, you see that curve has value that go from probably 0 to about 21. So it's a wide range, while the ensemble in this specific case, the red line, it goes from say 16 until about 19. So the range of values is a lot smaller. Yeah. So I think that's fine. And now this is an example of tropical cyclone Idai. So that was about a couple of years ago. And I plotted this one specific to show a couple of things. One of them is again the breadth of values, the range of values, and the consistency. So how much the ensemble is forecasting the same from the longer range to the shorter ranges. So if we're looking at the first example here, so you see here the curves. So the climate is actually right here, right, very, very close to the y-axis. You can see just about see it. So you can see that the forecast range is the one that were more kind of in the past forecast ranges, so the kind of like 108 to 132, so it's 6 to 7 day forecast, we're actually very much in line with the forecast. Sorry, with the climate. You see the distance between the bluish line and the black line is basically no distance. Okay, and you can see reflected here in these last few values here, the EFI is actually very small. Yeah, as you progress and as you get closer to the actual event, then you see that these curves are moving further away from the climate. So the red curve, which is now the latest forecast for this specific case, the EFI is 99. So the EFI is 1 basically. Okay. And this is for precipitation, and this is the same, but now looking at the wind gust. Obviously, tropical cyclone also wind gusts of some relevance. Yeah. So what you see here, it's first of all that the ensemble, as the event got closer and closer, the forecast was more and more extreme. Yeah. But the event itself was not forecasted 7 days ahead. So 7 days ahead, obviously the ensemble did not have any information about the fact that potentially there was something severe in the area. Yeah. But as you progress towards the verification time, so when the event is happening, is actually sort of indicating the strong, the indication of a severe event is getting stronger. So you see here already at, I would say, probably maybe 45, 2 days, maybe three days ahead, or maybe even a bit more than that, you can start seeing that the EFI is ramping up. Yeah. While for the and similarly for the wind, so you have a very similar signal on this one. Now, what you can see here is again what we were discussing before, the breadth of values. So if you look at this purple line, it goes from 0 to 400 millimeters. So you know the range is massive. So that means that the 51 members, they had very, very, very sort of large set of values, and this one gets smaller as you get closer to the event. So the latest forecast, it goes from about 100 to 250. Still quite a lot of spread, but a bit less than what we had in the previous forecasts. And similarly for the wind. The next slide is our fantastic group, and this one is another case which I picked up from Europe. This one it's actually not very recent, but it just makes another interesting point on this specific one. It's actually snowfall, which is absolutely relevant for Africa, I guess, for most places, but it does make an interesting point, and that is, so this is again, you see that this is the breadth of this is the number of forecasts in the past, so it goes up to 180, so 7 days, no, nearly 8 days in the past. So this forecast here will be the one 8 days before the event, and then as you get closer to for 24 hours before the event. So you can see here that you have the red line, which is your current forecast, is actually going back. So you have earlier forecasts that actually indicate that the event might be severe. They're still severe because obviously the climate distribution is somewhere here, still severe, but you see that the forecast has gone back, showing that maybe severe, but not as severe as expected. So this is like an example of what may happen. So you, on the one hand, you have pictures like this. Oh, yeah. Okay. On the one hand, you have a picture like this, where you have your red line, which is the latest forecast, progressively intensifying the event in the forecast. And then you have a situation like this, where it's progressively intensify, but as you get closer, it's actually going back and thinking maybe it's not that as severe as it is. So again, this one is again a way of looking at how consistent, say, the forecasts are. I think this was the last stuff that I had, and then I was going to try to see if I can just show you a little bit from the website. Share screen. Okay. Okay, we're going on the website, and what we're going to do is we're trying to see the connection between the EFI, CDF, and get some information about the consistency of the forecast or the uncertainty within the ensemble. Yeah. So what we're going to do, we're going to pick up a place in Europe. This is simply because the EFI is particularly intense in this day, but this one is valid for any, as I said, for any place in the world. So you see here, this is, so we are in the UK, so me and Becky are here, and this one is sort of Scandinavia, sort of moving north. So the event here is, we are looking at precipitation. And we have selected here.
I didn't find any events about here is looking at precipitation in the next 6 days.
Sorry, this is my phone talking to me.
That was very funny. That's serious.
You know, these phones, they talk to you all they listen to you all the time. So this is, so because we are expecting this to be a severe event, so we are looking at the climate distribution. We are looking at the, say, let's be a bit less ambitious, and we're looking at the 90th percentile. The 90th quantile. Okay, so this is kind of this area here. So here there is something I would say maybe between 2 and 10 millimeter of precipitation over the 24 hours. So what it means here is that the EFI is giving us a signal that definitely, not definitely, but very likely we'll have precipitation which is above these numbers that we have in the climate. Yeah. Okay. Now, because we can't do the clicking on this map, we have to go back, unfortunately, to our home. I guess hopefully home is the right home. And we click on precipitation because that's what we were looking for as a, okay. And then here you can see that this location here is actually indeed the same as where we had this very strong EFI signal. So if I click on this location, yes, I get an EPS gram, first of all. And this is my wind speed, this is my precipitation here. Yeah. So now, because we are interested in linking the map of the EFI to the CDF, we're actually going to look at the CDF. This is like demo, so hopefully everything works. Okay, and here we have, this is how we then link CDF, sorry, EFI to CDF. So here we have now the CDF for 24-hour precipitation, yeah? For different forecast ranges, the red one being the closest to us, so the latest forecast range, the latest forecast range. And we have the black line, which is the climate. So the black line indicates the climate for that specific location, which we had looked at, which was in the north of Europe. So you see the forecast, all the forecasts, they are very close to the climate line, the distribution. So the EFI is indeed not very big. This one is 15%, that means 0.1 in the kind of things we looked so far, and would be later on is 0.3. So on the maps you see, because we just start coloring at 0.5, you wouldn't see anything in this forecast range. So day 4, day 4 and a bit, day 5, and so on. Okay. So, but in recent forecast, there is obviously a signal for something a bit more exciting. Yeah. And you can see that the red forecast is actually quite away from the climate forecast. Yeah. So the EFI is 1 for the red, but the EFI is also 1 for the purple line and is also 1 for the blue line. And this is because all these 3 distributions are actually really, really distant from the climate. And we said the EFI is only calculating the climate, the area between the climate distribution up to this point here, which in this case is about 11 millimeter. So anything that is away from 11 millimeters, so like the blue, the purple, and the red, the EFI will be automatically assigned to 1. Yeah. So it's definitely the event described by the forecast is definitely more severe than anything related to the climate in the area. So this is 1. There's not one single value within this blue line, purple line, a red line that are close to any values in the climate for that specific location. Yeah. And you can see that the forecast is being quite consistent in the sense that it has indicated the progression of this severe event getting stronger and stronger and stronger as time goes. The range of values is quite large, especially for the blue one. It goes from 11 till about 40 something, 45. So it's quite a broad number of precipitation values. So if you had to forecast, you would really be struggling. And this kind of broad number of values is actually decreasing slightly as we get to a closer forecast. So it goes from nearly maybe 27 to about the usual 43 or 45 or whatever we have. So it's actually sort of narrowing down the values by making the line slightly more sort of vertical, but still the number of the values is quite broad. Okay, and then we can do exactly the same trick here. So if we are looking at the threshold, say we are looking at threshold of, I don't know, something easy, say 30 to 40, 35 maybe. So we are looking at the threshold of 35 millimeter of precipitation over the 24-hour period. So we have 35, we go back, is 40%. So we have a 40% probability of not exceeding the threshold of 35 and 60% probability of exceeding the threshold of 45. So you have 40% of your members, I mean, nearly half of your members, a bit less, saying that the precipitation will be less than 35, and 60% of your members saying that the precipitation is going to be more than 35 millimeter. And this is how you go from your EFI with your colored map, how you go to a CDF, how you go to your thresholds. Yeah, with some consideration of the consistency of the forecast, some consideration on the uncertainty linked to the number of values that are predicted by the ensemble. I mean, how the curve is slanted. Okay, so is this more or less clear? I think this is about what I wanted to say, but I would really recommend you to ask question now, because this is the moment when we can clarify all your doubts.
Thanks very much, Anna. Hopefully that was helpful. So we've got about 20 minutes left of the course, so probably about 15 minutes for questions or comments. If anyone would like anything clarifying or has any questions, that's what we're here for. We're here to answer as many as we can. So either please raise your hand or write in the chat, and we'll do our best to answer them. I can't see any at the moment.
Okay, until the other participant maybe prepare their questions and the thing that they wanted to be clarified, I can just ask if Anna could revisit this issue of the probability of not exceeding. So could you just touch on it again?
Yes. So what I'm just sharing the screen and I'm sharing exactly the same plot. Yeah. Okay. So this is, so here is your, this is what we done in the exercise in previously. So here you have the values of your, in this case, parameter, which in our case is precipitation. And here you have the probability. So in the exercise, we did the ranks, and then from the ranks, we work out the probability. So if you any of this value here is the probability of not exceeding a threshold, and the threshold will be set by the value of the parameter. Yeah. So for instance, if I go to 20%, so this will be the 20% probability of not exceeding, and then I follow the line of not exceeding the value of 33. Say it's 33. Yeah. So that means that you have 20% of your members produce values less than 33. 20% of your members is about 4, I think, in our ensemble. In other ensemble is different. So you have, say, 4 members of your ensemble that tell you the precipitation is less than 33 millimeters per 24 hours, I think, 24 hours, yes. But that means that if you only have 4 of those members telling you that, it means that the other 50 minus 4, 46, they're actually telling you that there is more precipitation than 33. And that is the 80% above. Is that clear?
Yes, very clear. Thank you very much. Yeah, it's
more
clear.
explanation about x-axis.
X-axis, this one is the amount of precipitation. So it's like 20 millimeters for 24 hours.
Sorry, I mean
Y-axis, this is the probability of not exceeding a specific threshold. So if you remember in the exercise we did, on this axis, initially we had ranks. So we order our values and each value had a rank, and we put the ranks here. And then we converted the ranks into probability. So these are the probability of not exceeding a threshold. Yes, no, yes.
Yeah, it's clear for me. Maybe someone else, if they have more questions, you can have the floor.
So yeah, I can make another example in the meanwhile, because the 80% seems to be right, easy to do. So here we have 80% probability of not exceeding, and then we walk along this curve, and we end up in this for the latest forecast of not exceeding the value of 40 millimeters over 24 hours. Okay, so it means that we have 80% of the members of the ensemble that have precipitation below 40. So 80% of the ensemble is about 46, we said. So 46 members of your ensemble, 46 out of 50, actually have precipitation below 40. But you have 4 members that are even more extreme, yeah? And they tell you that actually in this case, they forecast 4 values above 40. There was one question, is it this one?
I've got one here. The more, So it says the more forecast closest to the real time, the more it probable to occur. So that's Hussein, I think, saying is that the closer the forecast time, the more likely it is to occur.
Well, yes, in general, yes, because you expect that the shorter forecast or the closest to the real time are actually the more accurate. But you've seen that there was one example where I actually showed that this was not exactly the case. So in general, yes, we would expect that the shorter forecasts are more accurate than the forecast issued a long time in advance. So what we usually do, when we look at the events, we never do forecasting, but when we look at the event in terms of analysis, so we use the information that we obtain from the forecasts that are more distant from the real time. We use them as a warning signal, so that we start actually looking at the area as the forecasts are getting closer to the real time. So say if we spot something today that will happen in 10 days time somewhere, we don't disregard it because we say, oh, anyway, it's not going to happen, but we actually make an effort to every day as we progress towards real time, the famous 10 days in the future, to check in this location where there is something happening. Does it answer your question? Hussein, does it answer your question?
Yeah.
So the fact that in the forecast in the past, or the more distant from the real time forecast there is a signal, it shouldn't be disregarded. But it's a warning signal, so you may decide to follow it up and then see whether it actually was just something not there, or if something that is actually intensifying.
And also, I have one question I want to ask. In EFA, we can only use this index when there are extreme situation, or
yes. So the EFI, is not for normal forecasting. The EFI is specifically for extreme events. So this is the beauty of the EFI, is that of the EFI in terms of map coloring, is that it will just highlight places in the world where there might be something in the future. So you just then you don't need to look at the maps every day, everywhere, but you just focus on the location where the EFI is giving you a warning signal. But it's simply only for extreme weather. And you obviously then have to complement it with additional products, but the EFI is a warning index.
I have also one question, but it's a little bit different. I want to ask, can we get access to the ECMWF product apart from the WMO login? Apart from WMO login, can we get access to the ECMWF product?
Yes, so there's two ways of accessing ECMWF product. We have a way of accessing the kind of chart version of the product, which is probably something that you might be interested in. And this is so you would be that we have a license for this, which is about 1,000 euros a year, and this gives you access to our visualization tool, which is called EC Charts. And with this one, you can just visualize and customize and zoom and whichever maps you want. So you basically create your own maps, and you can create within the maps, you can actually make dashboards. So you have, for instance, the extreme weather dashboard, where you have all the products related to the extreme weather, so to help supporting extreme weather forecasting. So that's €1,000 a year. And then we have, if you're interested in data, then we have a set of data which is free for WMO, but the resolution is relatively coarse. And then we have licenses with different level of costing, depending on what parameter you get for non-commercial use. That means that you are using the data for your own duties, say. So you can't make commercial stuff that you sell, basically. Yeah. And this one is, you would need to contact us because it's a bit difficult to give you a price, but I think the max you can pay is about €42,000 per year. But this one, it means that you are going to be able to use the data. So you really use the numbers, and then you use the numbers for whatever you're doing. If you just want maps, then I would suggest you just use EC charts.
Great, thank you very much, Anna. Has anyone got any further comments or questions? I can't see any in the chat, and I don't see any mics open or hands raised.
So, okay, I'll ask. This is Abu Bakr. Okay, to Anna, I wonder if you are a forecaster and sitting, for example, at the airport or like you are serving disaster risk management authorities or something like that. So, in case of this, the case you have shown, that is, for example, there is an 80% chance that the rainfall will not, for example, the case of rainfall, you have 80% of not exceeding beyond some certain threshold, right? And then you have another maybe 20% that is the rainfall might exceed that threshold and become extreme. So four members, for example, against 56 member of the ensemble. What would you advise in that case? So, for example, should the forecaster say, okay, I have 80% chance that the rainfall will not exceed this threshold, I will issue that and ignore the other 20% or minimum, or not highlight it? Or which direction would you advise operational forecasters to deal with this, to issue their forecast?
Okay, so this is a question probably more for Becky than for me, because I've never really did the proper forecasting in the sense of, having. I think it will depend very much from your customers, so the people who are using the forecast, because obviously this is, there may be some businesses very high risk, they cost very much. If something wrong happens, the losses are massive. So then you would probably think, okay, maybe it's better if I'm very cautious and I sort of tell them not to do something, even though the probability is very low. But there may be businesses where the loss is actually going to be minimal. And then you would say, okay, even if this happens, this is very low probability, it's more likely that it's not happening. So I will go for telling them that it's not going to exceed that threshold. I think it depends very much on the businesses your customers. So maybe Becky here, you can be a bit more, you can elaborate a bit more, because you've been doing impact forecasting. So
yeah, so I did do impact forecasting for quite a while, and I fully agree with Anna. It depends. Every customer and every person has their own level of risk, so what they are willing to accept. One thing to think about, to use as well, as your experience with the data itself. So if you know a forecast is a very high rainfall totals don't happen very often, it's an idea, keep an eye on it, but maybe don't say that a week in advance that there might be 200 millimeters of rain at the end of the week. Just keep an eye on it, because your experience will probably tell you that that's not very likely. However, you'll find when you talk about the likelihood of things on TV forecasts or even in documentation, the words likely, unlikely, very likely are used quite a lot. So these are kind of terms that encompass sometimes you can put probabilities behind them. I know WMO tried to do it. They said, I think 80% chance was, up to 80% was very likely, and then you got up to 99%, which was extremely likely. So they turned the percentages into words, and those words actually for customers allow them to assess what risk that they're willing to take. So if I hear a forecast of it's very likely to rain, I will take my umbrella with me. If it says it might rain or a few showers, I'll probably not bother with the umbrella because it's an extra thing to take with me. So I think it's giving your customers, you understand your customers better than we do because you're the ones talking to them. So it's understanding what they need to know and using that judgment in order to provide them with the best forecast. Now, telling them that there is also one ensemble member that is gone very extreme, as we saw in the box earlier, and also with the EFI, saying that I don't think is a detriment. It makes them aware that there is always a chance of something that might happen, but it's very likely to be between kind of a lot lower bounds. So that's what I'd recommend when you talk to customers. Really ask questions, understand them, understand what they are using their forecasts for, and what thresholds actually potentially matter to them. If they're high likelihoods of rain, potentially, so maybe they want to know when there is even a small chance of really high rainfalls or strong winds, for example. So it's just about really understanding your customers and using your experience of both the models and your customers. Hopefully that helps at least a little bit. So we are getting towards the end of the training. We've got one more question. If there is not a difference between the ensemble forecast distribution and the model climate distribution, how can I explain this situation? So if the ensemble forecast is along the line of the model climate, the model climate is generally a larger range. If the forecast is tracking it, there will still be some extremes at one end of the model climate, as we've seen earlier. If there's not a difference, you explain it saying, and kind of take the model climate out of it and try and explain it to how you would just a normal forecast. There's a large range. It's uncertain what will actually happen. You look at different products, so not just the CDF. Start looking at the rainfall products. Start looking at whatever other products will help you try and interpret and make your best judgment of what happens. As we discussed earlier, the high resolution and control members are two slightly different model runs. The high resolution is higher resolution. So you kind of may look at that a little bit. The control run, it gives the best guess. However, you should take it with all the ensemble members as well. So I'd suggest in that case, looking at different model outputs and seeing what else is going on. I don't think I've ever seen the distribution track the model climate.
Oh, it does sometimes.
It does sometimes. Okay.
But the key point here is that because the EFI will not show. Yeah. So you will have no indication of the EFI. So it's very unlikely that you are actually going to find that plot. To check that plot and to go and have a look at this at the CDF. So the idea of looking at the CDF is really just, you look at it when you see that the EFI has got a signal. So I wouldn't just go and see all the CDFs every single day for every single location, because it just a waste of your time, to be honest.
Yeah, you really want to look at those extremes like we've shown earlier, and just commenting as well, the shift of tails tells you how extreme those extremes are as well, as we did mention. Okay, so we are getting towards the end. So thank you all very much for attending. We hope you found it helpful. Now, with every course, I'm sure you're aware, we do like to gather feedback. So in the chat, I've put a link to a SurveyMonkey quick survey. It should take only, I think, 3 to 5 minutes, just asking how you found the course. This is the first time we've run this course. Mainly because Open Charts only went open in October. So it's the first time we've put together a course like this, focusing on Open Charts, specifically on EFI and meteograms, because now you have access to an awful lot more than what you used to. So we'd really appreciate your feedback. The the link is in the chat, and then I'll also send it to the hosts to send out to all participants afterwards. We'd really appreciate you filling it in and providing any information, however small you think. Every piece of information helps us to make these courses better and improve them. There is also another question about a potential, another kind of probably a similar time length, so another day in a few months' time, where we would get everyone back together, ask how you've used EFI in your and the meteograms in your day-to-day work, and answer any further questions. And we've got some ideas of what we could do in another kind of part of the training. So there's a question in the survey about if that would be something you'd be interested in the future as well. So with that, I will say thank you all very much. Thank you to the hosts at ICPAC for organising it, and for you all for attending, and for your questions, and we hope you found it interesting.
Bye, everybody.
Thank you very much.
Thank you.
Yeah.
Thank you very much.
Yes.
Thank you. Thank you, everyone.
Bye.
Yeah,
Bye-bye.
please, before you leave, try to complete the courses, the online courses, and
yes.
try to use.
Bye-bye.
Thank you so much. Thank you.
Good. Thanks.
Thank you.
Thank you all. Have a great rest of your day. Thank you for your messages in the chat as well. It's lovely. Bye. Thank you.
Becky,
Yes.
maybe if you could copy the chat, that if you are interested in some questions, and maybe also could be
Oh yeah,
helpful
I can save
before.
chat.
Yeah, before we close.
Yeah, I've got the chat as well. You've recorded it as well,
and then
haven't
you can, you can share with. Did you said the link, right? Could you pass me the link for the survey?
Email you the presentations, and then the link to the survey to send out as well, and we can have another discussion.
All right, copy. Bye, Anna. Thank you very much. Really appreciated your effort, you and Becky and Ismail. I all have a bit of difficulty pronouncing the name of Esperanza.
Esperanza.
Esperanza. Okay.
Yeah.
Sorry for that. We have difficulties in names. Esperanza. The African names are also difficult for Becky. So
yeah, you heard my African name pronunciation was.
We're even.
I tried.
Esperanza. Great. It's really nice of you. Thanks to all of you.
Thank you very much.
Thank you.
Thank you very much. All right. Okay. I will close the meeting, and we keep in contact.
Yeah, definitely. Thank you all very much.
All right. Thanks a lot.
Thank you.
Have a good day.